My name is Ping Wang. I'm from Computer Science Department from Stevens Institute of Technology. My research focuses on AI for healthcare and social science. Specifically, I'm working on information retrieval from different databases with natural languages, information extraction from unstructured text, and predictive analysis. So tomorrow we are also going to have a presentation by my PhD student about medical term coding. So if you are interested, I'm happy to talk more. Okay, come back to the session. So this session is about evolutionary and longitudinal patient and disease models and personalized medicine and preventive treatment. So compared with other sessions, we have more papers. We have 7 papers, long papers. So we need to finish all the 7 presentations in the same time. So that means for each presentation, we are going to have around 10 minutes. Okay, so when there's 1 minute, I'll give you a reminder. So let's welcome the first speaker, Trusting Inequity. The title of the paper is A Genetic Neural Architecture Search Framework to Predict Biomarker Status in Cardiovascular Disease Patients During Pandemics.
Thank you so much. My name is Trusting Inequity. I'm a PhD, sorry. I just got my doctorate yesterday, so thank you. I'm still getting used to it. So the title of my presentation is A Genetic Neural Architecture Search Framework to Predict Biomarker Status in Cardiovascular Disease Patients During Pandemics. This is a work I did at Worcester Polytechnic Institute in collaboration with UMass Medical School. The motivation behind my work is pandemics. Pandemics are global outbreaks of infectious diseases that could increase morbidity and mortality. An example we see is the COVID-19 pandemic, which is caused by the severe acute respiratory syndrome coronavirus 2. Symptoms of this disease include fever, cough, difficulty breathing, fatigue. As of May 2024, the World Health Organization declared over 700 million cases and 7 million deaths. Studies reveal that patients with chronic disease were more prone to infection and, in worst cases, mortality. An example of chronic disease patients are cardiovascular disease patients. Cardiovascular disease refer to heart-related diseases, for example, stroke, hypertension. These patients were directly impacted via lifestyle changes, for example, no physical activities, unhealthy diets, and indirectly via the lockdown measures, which disrupted their needed routine care. And so the goal of my work, of this paper, was to examine pandemic impact on CVD patient biomarkers. Biomarkers are measurable indicators that doctors collect in hospital settings, and they provide insights into a patient's health status. And so CVD biomarkers are biomarkers used to provide insights into a patient's CVD status. For this study, we evaluated the pandemic impact on 2 CVD biomarkers. One was low-density lipoprotein cholesterol, which is the level of cholesterol in the blood. Incrementing this could generate plaques in the arteries, which could prevent blood from flowing. As well, the other biomarker was glycated hemoglobin, which indicates the level of sugar in the blood. Abnormal values of these biomarkers revealed poor health outcomes in CVD patients during the COVID-19 pandemic. And so the problem we tried to solve was something we observed. First of all, we saw that prior approaches to examining pandemic impact used shallow machine learning models. So shallow machine learning models include models like decision trees, random forests, linear regressions. However, these approaches struggled with predicting impact because they were limited in their capabilities. And also, when you're using electronic health records, these health records are usually very heterogeneous in nature. And so these shallow machine learning models were not able to really capture the patterns in this data set well enough. On the other hand, deep learning models can give you improved results, but it requires some sort of expertise and effective model. And tuning, which is generate optimal hyperparameters. When I talk about hyperparameters, I mean configuration passed into this deep learning model to give you optimum performance. This hyperparameter tuning is usually manually done, which could hinder generalization and could be very time-consuming. To generate a deep learning model that could predict CVD biomarkers. AutoML, or automated machine learning, is a broad subject, and so specifically, we're interested in neural architecture search, which is an automated means to come up with an ideal set of hyperparameters. Examples of neural architecture search were evolutionary or genetic, reinforcement learning-based, and graded-based approaches. The choice we selected from this study was genetic algorithms or evolutionary approaches because we've seen extensive healthcare applicability. Genetic algorithms are also flexible. The space of solutions in genetic algorithms can be evaluated in parallel, and this could they also use improved exploration means. And so the research questions were, how accurately can the evolutionary approach predict CVD biomarkers during the pandemics? What were the important features for predicting CVD patient biomarkers? We're interested in social determinants of health like age, race, gender, and socioeconomic status. But before we went into the specifics of what we did, related works revealed that evolutionary approaches to estimating pandemic impact was generally centered around CVD detection on spectrogram image, COVID detection using image data, and COVID detection on text data. A limitation overall we observed was the applicability of genetic neuroarchitecture search on electronic health records in COVID context and for CVD patient biomarkers. And so the goal was to leverage genetic neuroarchitecture search to create a deep learning model that could predict pandemic-induced CVD biomarker prediction using the electronic health records. Before I go into the details of the methodology, just wanted to say we collected electronic health records from patients treated at UMass. There were over 80,000. We did some data cleaning, data restructuring. We selected pre-COVID pandemic onsets and during COVID timeframes. Pre-COVID were dates from January 1st, 2019 to December 31st, 2019. Pandemic onset was March 10. This was the period when the governor of Massachusetts declared a pandemic in Massachusetts. And then during COVID was June 10, 2020 to June 10, 2021. And then we selected patients with CVD using the 10th International Classification of Disease Code. And then from the 80,000, with all this data processing, we had over 50,000 patient health records. The methodology, as I mentioned earlier, we collected health records, and then we used genetic neuroarchitecture search to come up with an ideal set of hyperparameters. Genetic neuroarchitecture search has three main components. One is a search space, the second is a search strategy, and then each potential solution in this search space is evaluated using a performance estimation strategy. The goal of neuroarchitecture search is to find an optimum network architecture within a search space where the search space contains all possible combination of solutions. So they find an optimal neuroarchitecture, a network architecture within a search space with respect to validation loss, validation data set, and weights which are derived from minimizing the training loss and validation loss. So the genetic neuroarchitecture search strategy or process is you start with a population of potential solutions. Each individual in that population is, their fitness is evaluated, and then the best are selected. Then we perform evolutionary operations on these individuals, and again, they're evaluated, select the next criteria, the next generation. If the stopping criteria is met, then we stop, or it's an iterative process to identify the last population and the most ideal solution. So a step-by-step approach, collected health records, processed it, applied neuroarchitecture search means, generated the best set of hyperparameters, passed as a set of configuration to this deep feed-forward neural network model, and then we passed the preprocessed data to the neural network regression model, and then we made prediction on the two biomarkers. Input features were age, gender, race, income, period. Period was before pandemic and after pandemic. blood pressure, BMI, and then target features were HbA1c and LDL cholesterol. Abnormal values were given as 1 because we did classification, and normal values during the pandemic was 0. For neuroarchitecture search input parameters, search space was 20 individuals, and each individual comprised number of layers, number of neurons, activation function, optimizer. The values you see in the parentheses are basically the different possible combinations for each individual. So an individual could have 2, and then the number of neurons could be 16, activation function could be tan-H, and things like that. Search strategy was genetic algorithms, and then we evaluated using accuracy, F1 score, precision, and recall. For our finalized model, we compared to shallow machine learning models, and then we also compared to other baseline neuroarchitecture search approaches. To interpret our model, we use Shapley values. So what we observed overall was a genetic neuroarchitecture search had very high performance. It also generated an ideal set of hyperparameters that you could use for HbA1c prediction. And when we compared to shallow machine learning models, also had high performance. And we observed that income, age, and pandemic period were critical factors in predicting LDL cholesterol. So I only showed the LDL cholesterol in these results. And then the pandemic was linked to lower LDL values. So limitations in this study, we collected homogeneous participants from central Massachusetts, and they're predominantly white. We neglected things like biomarker interdependence, temporal nature, and we also failed to capture data and model uncertainty. And so future work will be geared towards addressing this. We also like to use interpretable optimization approaches like genetic programming, genetic trees. We'd like to see how genetics actually intersect with COVID impact on diverse human populations and also real-world applicability. Thank you.
Hello. So good afternoon, everyone. I am Jait S.A. India PhD student at University of Tennessee, Knoxville, working on intelligence system. I am excited to be here and share our work on pulse rate, a robotic wheelchair for personalized exertion control. So today, people with mobility impairments face significant challenges with just 2 options available: manual wheelchairs and powered wheelchairs. Manual wheelchairs are affordable and widely accessible, but they require a lot of physical efforts, which over the time can cause serious injuries such as shoulder injuries, etc. On the other hand, power wheelchairs make it easier to move from one place to another place, but research shows that these no to little activity often lead to a more sedentary lifestyle, such as risking obesity and cardiovascular issues. So this gap inspired us to think about solutions that will promote physical activity while minimizing strain and injury risk. So our key research questions was how do we design a smart wheelchair that will support daily mobility and also encourage physical activity? So we want this physical activity to be a natural part of everyday life, so that based on our recent research activity on lifestyle physical activity. But here's the challenge. Every wheelchair user has a unique profile. Think about BMI, age, heart response, strength, which shapes their physical mobility and activity needs. So here's where our pulse rate system comes in. On the right side, you will see our pulse rate system, which uses multiple sensors to collect heart rate, ECG, and velocity data. And an AI algorithm will decide when to turn on the motor to provide the assistance and for how long. Basically, our pulse rates AI algorithm divided into 2 parts: human in the loop reinforcement learning and reward function optimization. We will first talk about human in the loop reinforcement learning a little bit. If we take a closer look, we will see that human in the loop reinforcement learning framework's data flow starts with a pre-trained encoder. This pre-trained encoder was used to analyze ECG data. Before that, this encoder was first trained on separate ECG data, which was offline to classify high, medium, and low activity, helping us to understand the user's physiological state in real time. Then, after getting the ECG features from the pre-trained encoder, we combine them with the heart rate and velocity from the users and fed through a decoy algorithm, which then decides every 2 seconds whether to activate the motor or not and for how long. These actions persist for next 2 seconds before another decision comes from the algorithm. Finally, we will talk about our reward function that guides our pulse rate system's AI. The reward function used heart rate and velocity to divide performance into 5 regions. Here you can see that green for success with highest positive rewards, and 2 yellow zones for moderate deviations with slightly negative rewards, and the last 2 red zones for extreme cases, for extreme inactivity and intense exertion. We get the highest penalties to avoid those unhealthy states. The key things to note here, these regions are personalized and unique to each user. So building on our reward function, our next research question is, how does our approach work well for personalizing assistance? This focuses on tailoring pulse rate support to individual physiological needs, ensuring every user will have their customized experience. To address this research question, we conducted a series of experiments with 10 individuals without disabilities. We chose non-disabled participants to ensure safety, and also as we refined our system with a goal of utilizing them in our future studies. We also measured muscle contractions for each participant using an EMG sensors. Next, our experimental procedures consisted of three key phases: pre-training, training, and testing. The pre-training phase divided into 3 equal sequential segments of medium and high activity, gives us the advantage of designing each user's unique heart rate and velocity profile. At the end of this pre-training phase, each participant will receive their personalized reward function, which will shape both their physical activity and provided assistance at the later phase. After 1 to 2 minutes of break, each participant starts their training phase. They were mostly instructed to maintain a moderate velocity zone, which shows the moderate activity, which in this case is the green zone, except when prompted by a smartphone app on the left side, you can see, to slow down at 12 minutes or to push intensely at 16 minutes. We did this because these varied activities allowed our decoy algorithm to explore the possible wide range of user states to make it more generalized intelligent actions. So next, we conducted a 5-minute of testing phase for both pulse rate and manual wheelchairs to compare our results. So what we found is that pulse rate did a really great job on personalizing assistance for each users. If you look into this figure, you'll see that most users stayed in their green zone. That means that their heart rate and velocity were where we wanted, even though their target zones were different for everyone. We also found that pulse rate made a big difference in reducing physical effort. Muscle contraction dropped by 42%, which means users didn't have to push hard. In this figure, a lower orange bar means perform better, pulse rate perform better for each user, and the bars are different because of their personalized need. However, for some users, like user 3 and user 10, pulse rate focus more on keeping their heart rate stable instead of reducing their number of pushes. This shows us how our system prioritizes balanced exertion, adapting its assistance to each user's physiological need. But does pulse rate across different environments? We thought about slate, carpet, sand, and grass. But at the end, we chose slate and carpet environments for our experiments. Our results show that pulse rate really shines here. When it comes to different environment. We trained the system on slate and tested on both slate and carpet, and it did really perform well on maintaining the heart rate in the green zone for most of the time. In contrast, for the manual wheelchair, the manual wheelchair users spend most of their time in the higher exertion, as you can see in this figure on carpet. So this demonstrates how pulse rate can adapt and provide effective assistance even in more challenging environments. Additionally, fatigue is a huge barrier for wheelchair users. Our EMG analysis shows that pulse rate maintains a positive trend in mean frequency, which means muscles stay fresher for a longer period. On the other hand, manual wheelchairs, where fatigue sets in faster, so this means pulse rate provides a longer and more comfortable mobility for users, enhancing their daily lives. So now in summary, pulse rate delivers on its promise, personalized adaptive assistance that promotes health and reduces effort. The layout plus on the right side shows that despite limited training data, our algorithm learned effectively. So in our next steps, we are partnering with wheelchair basketball players at Christian Berry Community Center in Knoxville to test pulse rate in real-world athletic settings. We are also exploring some advanced algorithms like actor critic method and PPO along with continuous motor control to make assistance even smoother. Finally, we are working on a more compact version of the pulse rate system, aiming for on-device computation to run everything right on the wheelchair. So thank you for your attention. If you have any question, feel free to ask me. I'll be there for all of the time. Okay, thank you.
Thank you. As we mentioned at the beginning of the session, so we have more papers in this session, and we will save all the questions at the end of this session. Okay. Thank you for the presentation, and let's welcome our next speaker. You the first one. Xiang Xinguo. The title of the presentation is State-Specific Explainable Machine Learning for Predicting Premature Dropout in Medication for Opioid Use Disorder.
Hello, everyone. I'm Xiang Xinguo from University of Texas at San Antonio. It's my honor to represent our team to present our work, state-specific example machine learning for predicting premature dropout in medication for opioid use disorder. Before we start, let me introduce some background knowledge. Opioid use disorder is a clinical and relapsing brain disorder. And the most acute and life-threatening consequence of OUD is overdose. When overdose happens, it can cause brain damage, coma, or the death. And OUD is a global health crisis. There are more than 60 million individuals affected by OUD in the world, and there are 2.1 million Americans with OUD, and there are more than 80,000 opioid overdose deaths in US in 2022, and the economic burden is the $1 trillion in the US in the 2017. Fortunately, we do have effective treatments for OUD. It's the FDA-approved medications like the buprenorphine, which can reduce athlete opioid use and decrease overdose mortality. However, the critical success factor is that the success of treatment heavily depends on the adherence to the treatment, and patient may premature drop out from the treatment before achieving stable recovery, which can increase the overdose risk and increase the health system burden, and patient may return to the athlete use. So here come to our motivation. It's the geographic region difference. In the left side is a map showing the buprenorphine dispensing rate. The dark red states have the highest dispensing rate. However, in the light color states, it has the lowest dispensing rate. In the red figure is the MUD treatment premature drop rate across the states. These two figures reflect that there are underlying differences in healthcare system treatment practice in different states. Now let me introduce the objective. Even though the machine learning is used to predict who is at risk of premature dropout, however, the most operators overlook the geographic variations and also the lack of its mobility. So to bridge this gap, we propose the state-specific explainable machine learning framework, which captures both shared patterns and unique patterns to improve the prediction accuracy. To achieve our objective, we use multitasking learning. Multitasking learning is advanced machine learning method. It's that learning multiple related tasks at the same time for best performance, and it works well in our situation because the MUD premature dropout in each state shares the underlying patterns, and each state also has the unique factors like the social, economic, and policy that influence the treatment outcomes. So now let me introduce the framework we proposed. Given the patient representations, including demographic information, social income information, and substance use history, it first goes through the shared layers, which are shared by all the states to capture the general factors that influence the treatment outcome. And then we design the task-specific layers for each state to capture the state-specific factors. And then finally, we have the explainable model to for the making decision. Now, it's the mathematical foundation of our method. Overall, we minimize the sum of loss of all states, and each state has have shared parameters and also their state-specific parameters. To evaluate our method, we use the treatment exposure dataset discharge. It's the dataset collected by the U.S. State Administrative System, and we carefully select the patients that only include the adult patients and confirm the diagnosis with all period use disorder, and for the patients receive the MOD treatment. The target wearable of our method is the premature premature discontinuation, which means that the patient leaves the treatment early for reasons such as the unknown cases or being lost to the follow-up treatments. And we have totally 25 practical variables like the demographic and the social economic factors, and also the substance use habit and history, and also the treatment information. We compare our method with two baselines. One is the state-specific models. For each state, they train their own models using only their local data. And for the another one is the one-size-fits-all model. We only train a single model on the data from all 20 states. And finally is our proposed method. As we can see from the results, our method perform better, outperform our baselines, which demonstrates its ability to capture both shared and also the state-specific factors to improve the accuracy. And the final is the wearable accepts of our framework. It's the feature. This heat map showing the feature importance across the different states. Each row is the input features, and each column is the different states. As we can see from this figure, some factors are universal for all states, but some features are state specific. I summarize here. For the mass frequency of substance use is a universal predictors, and like the veteran states, it have high impact in CAAR. And also for the vehicle use, it's have the notable impedance in VT and MA. So these these findings suggest that the target interventions should consider specific factors like the veteran population and the co-occurring vehicle usage in the opioid use disorder. And here is the conclusion. We propose the multi-task learning framework to protect the MOD treatment and use the experimental model for practical operations. However, the limitation of our method is that the dataset is personal level, not the patient level, and some features rely on the recall. So in the future work, we will integrate the social determinant of health factors and explore more advanced methods. That's all. Thank you. Yeah.
Thank you. Thank the speaker. And let's welcome next speaker, Matthew Clark. The title of the presentation is Predicting the Severity of Anxiety in Adolescents Through Passive Resistance Behaviors.
Hello, everyone. I'm Matthew Clark. I'm here to talk about our paper. So as we know, anxiety disorders are very prevalent. Estimated that they affect 301 million people in 2019, and studies show that the number has likely only increased in recent years with events such as the COVID-19 pandemic. And experiencing severe anxiety during adolescence can be particularly detrimental to one's later life because it can impact the mindsets and behaviors that form and carry on through the rest of your life. Mobile health systems have been proposed to target adolescents' mental health, but they don't always leverage passive sensing to passively monitor the user. And when they do, they often focus on unimodal data or a mental health disorder that is not anxiety, such as depression. So in this work, we collected weekly anxiety reports and passive sensing data from 55 participants over a period of 24 weeks. And we then used the behaviors to predict the adolescent's anxiety each week. Based off the timing of the study, we also do some analysis into participants' anxieties and behaviors during the early stages of the COVID-19 pandemic, but I'll get more into that later. So this work centers around the user study. So what happened was all participants were provided with a Fitbit, shown there, and installed the app called Aware on their phones, which lets us record their phone behavior, such as screen time and location. Again, I'll go into more depth on this on the later slide. They also completed a weekly GAD-7 questionnaire, and onboarding for the study began in early March 2020, which coincidentally overlaps with the COVID-19 pandemic in the United States. So 55 participants were recruited. They're all adolescents, and the eligibility criteria were that they had to exhibit anxiety symptoms, own a smartphone, and be between 12 and 17 years old. So here's a picture of the GAD-7 questionnaire as it appeared in our study. So participants take each of these questions and rate how frequently that symptom bothered them over the past week, ranging from not at all to nearly every day. Their overall GAD score indicates how severe their anxiety is, from 0, meaning very low anxiety, to 22, meaning very high anxiety. In addition to predicting the GAD score, we also created models to predict their responses to each individual question, gaining further insight into how each participant's anxiety was manifesting. Additionally, the GAD-7 also lets us break it down into these more discrete, more concrete categories, and we predict these as well. In terms of the behavioral features, we extracted them using RAPIDS, which is a framework that lets us get interpretable features from time series sensor data. And each of those features is described for the entire week leading up to when they filled out the GAD-7 questionnaire. We extracted 142 features total, describing their phone calls, text messages, locations, screen time, Wi-Fi connections, activity recognition, and also physiology, such as their sleep, steps, and heart rate. We did do some basic cleaning and imputation on here. I can't go into too much detail, but we removed features that were missing more than 75% of the samples, and then we imputed what we could using the known values from adjacent weeks. So starting off with the predictive results, we created personalized models for each user, so predicting each person's response, each person's behaviors were only used to predict their own, using a leave one, week out cross-validation. The random forest regressor, predicting GAD-7 scores, achieved a mean absolute error of about 2.45, which on a 22-point scale means that it's getting in the right area, maybe not precisely correct, but it's still giving reasonable insight into how anxious each participant was. Then we used random forest and AdaBoost classifiers to predict the anxiety level and specific questions. If you want to know why we use these, I unfortunately can't get into it, but so the overall anxiety level achieved about 58% accuracy, whereas the responses to individual questions ranged from 52% to 63%. All of this is well above random chance at 25%, which is indicating that we are able to make these predictions for adolescent participants based on their behaviors. We also looked at the interpretability of these models using feature importance. Specifically, we recorded the impurity-based feature importance of every feature across every fold of every participant's cross-validation, and recorded which features are most frequently appearing as important to the models. And what we found was screen activity and location features had the highest proportion of features appearing as commonly important. Phone calls were also fairly important, but slightly lower. What's interesting to note here, in addition to which sensors are important, are which ones were omitted. Specifically, we never saw any steps or text messaging features appearing as frequently important to these models. Now getting into COVID, as I mentioned, the study unplanned started onboarding in March 2020, and as we heard earlier in the session, lockdowns began around March 10th. So the study was run in Pennsylvania, and the way Pennsylvania handled the lockdowns were there were 3 phases. A total lockdown basically meant all businesses are closed, like curbside pickup. Partial lockdown meant some stores are reopening, and then minimal lockdown meant most stuff is reopened, just make sure you're still exercising caution. So we then compared the pairwise analysis to look for differences in anxiety and behaviors across these different lockdown levels. And what we found, interestingly, was that anxiety was actually lowest during the partial lockdown. We can only speculate as to why that would be, but we could see some influence potentially from participants feeling optimistic that the world is reopening from a complete lockdown, but still feeling somewhat safe that there are precautions in place still. But again, we can only speculate as to why. And naturally, we also saw differences in behavior. Most intuitively, participants took fewer steps and traveled less during the complete lockdowns. Interestingly, they also unlocked their phones more during partial lockdowns, but they didn't actually spend more time on the phone. They were just unlocking it more individual usage sessions. And we also saw that they spent less time lying awake in bed in the mornings during a full lockdown when they didn't have anything to get up and go do. And there's more in the paper, but I unfortunately can't get into it for time here. Then what we also looked at was how participants' behaviors and anxiety changed during the minimal lockdowns in relation to the number of new COVID cases during that same week. And we found there were some differences. Their anxiety did not relate to the number of new COVID cases, but their responses to the question asking them how fearful they were did. So they were not necessarily more anxious when there were more COVID cases, but they were more fearful. And then, of course, we also saw behavioral differences. In particular, participants spent more time on their phones when there were more new COVID cases. But interestingly, only 5 participants actually spent more time at home when there were more COVID cases. So just in conclusion, our work looked at predicting anxiety for adolescents using passive sensing. We found that this seems to be doable, especially using location, screen, and activity recognition features. And then we also looked at how participants' anxiety and behaviors differ between the different pandemic stages and number of COVID-19 cases at the time. Thank you for listening, and special thanks to National Institute of Mental Health who supported this work, and some of our lab's external collaborators who helped with it as well.
Let's thank the speaker and move on to next presentation. Let's welcome the speaker, Soumya Sri Sahu. The title of the presentation is Smartphone Data Gathered Early in Depression Treatment Predicts Treatment Outcome.
Good afternoon, everyone. My name is Soumya Sri Sahu. I'm a PhD candidate in computer science and engineering at University of Connecticut. Today, I'm going to present my paper on smartphone data gathered early in depression treatment, predicts treatment outcome, which is a collaborative work with the clinicians of Yukon Health. Today, I'm glad to share our findings with all of you. So depression can impact many aspects of daily life, such as the physical, social, or emotional functioning, and is also often associated with higher suicidal risk. So in the depression treatment, the primary goal of depression treatment is to help the patients to fully recover from their depressive symptoms and to regain normal functioning. However, the treatment does have certain challenges, such as only about 35% of the participants recover or remit after the initial treatment, and those patients who do not recover during the initial treatment, only about 40% get improved, if at all they pursue the treatment and switch to another alternative treatment. But in reality, many of the patients drop out early, and half of them return after the first visit. Therefore, there is a need of an early prediction of treatment outcome that can improve care and allow the timely adjustments to the depression treatment, so that we can avoid the prolonged suffering in the depressed individuals. So in this paper, here we mainly wanted to explore how we can use the data of the first few weeks, primarily the data from the first 2, 3, and 4 weeks data, how we can use it effectively to predict the treatment outcome at the end of the treatment course, that is at the 12th week mark, which is considered as the end of our treatment. And basically, we wanted to predict the treatment outcome 8 to 10 weeks in advance or earlier before the treatment ends. So smartphone provides a unique opportunity of collecting the data passively without having any active engagement from the participants directly. And it is also it does have lower burden on the participants as well for the data collection. So here, using our smartphone app, we have relied on 3 different types of data, such as 2 survey types of data, that is medication, daily self-rating, EMA, and the location sensory data. And along with that, we have also relied on the QIDS, that is the quick inventory of depressive symptomatology, which is self-reported again directly from the participants that we collect through our app. And it is it is considered as a comparison baseline and often used by the clinicians for assessment of depression. So in this study, we were able to collect the data of around 87 participants from January 2020 to June 2024. So from all the data sources together, here we have extracted various features separately from the different data sources. And again, along with that, we have also collected the QIDS score and the baseline QIDS score as well. That is collected during the first week, that is when the participant first comes in for the enrollment, we collect the QIDS score just once. And with all the data or the features that we extracted, we try to explore different combinations of the smartphone data separately and combinedly together, along with the QIDS baseline and QIDS score together, to predict the treatment outcome with the help of deep learning models, GRUD and BRIDS. So we have developed a smartphone app called Life Rhythm. that is able to collect two different types of survey data. So the first one is medication survey, which is collected on a weekly basis. The responses are to be submitted by the participants on a weekly basis. It includes three different type of data or features. That is adherence, safety, and tolerance. Adherence is mainly related to how are they taking the medication, whether regularly or not. Safety means it's related to the side effects to the medication, and how tolerability is how are they tolerating? Are they able to tolerate the medication intake or not? Next comes the daily self-rating data, which is again collected from our smartphone app, but on a daily basis. And here I applied the pre-processing on this daily data to extract the features on a weekly basis, that is specifically the mean and standard deviation of the mood and anxiety data, which we call it, which is often also noted as ecological momentary assessment data, so EMA. So further in my next of the following slides, I have used the EMA mostly to signify the daily self-rating data. Next comes the location sensory data, which is typically collected passively without having any active engagement from the participants. It has a multiple level of pre-processing, which does use the steps that I have already used in one of my other paper. So which includes the data of GPS, Wi-Fi, and activity data together to extract 8 different location features. Then the quiz data, which is used as a comparison baseline in the prediction. Next important thing is the ground truth. So for the treatment outcome or ground truth, so here we computed on our own, just relying or using the quiz data, that is percentage drop, which is calculated by this formula as shown here. It is based on the 12th week quiz score at the end of the treatment relative to the quiz baseline score, which is collected in the beginning of the treatment. So once we compute the percentage drop, if the percentage drop is greater than or above 50%, we label the samples as improved, otherwise they are labeled as not improved, and I used it as the ground truth in the prediction. Okay, so this was not included. Anyway, I have removed this slide because of the time limit, but anyhow. So to understand the correlation between different features and the percentage drop, here I have presented some of the correlation results using the week 4 features, which is considered as significant in the clinical scenario. That is the end of the early treatment. So here I found more, and the 12th week percentage drop. So I found these features to be highly correlated with the percentage drop. Now, since we are using the data of multiple sources, here we wanted to include the participants' data. Those are present for across all the different sources, that is medication, daily self-rating, and the location data. So to understand the extent of missing data, so these are the plot that shows when we include 2 weeks, 3 weeks, and 4 weeks of data in the prediction, how much amount of percentage of missing data that we have across the different sources. So here we found that in case of location features, it does have higher percentage of missing data in comparison to the daily self-rating, which is moderate amount of missing data, and the medication. We fairly found a complete sort of data in case of medication data in comparison to location and daily self-rating. So here in this work, the main challenge is to how effectively use the 3 different data sources along with the missing data and use it combinedly for prediction. Now, next is the prediction and the classification. So, specifically in this work, we tried to predict the 12th week treatment outcome, that is the relying on the percentage drop, including the data of the first 2, 3, and 4 weeks. So these are the prediction scenarios when we include, when we use just the smartphone data, when we include the quiz baseline score with the smartphone data, and when we include the week 4 quiz score and the baseline score with the smartphone data. So in order to handle the missing data, we have incorporated or used two different deep learning models which are specialized to handle the missing data and also performs prediction. That is GRUD and BRITS. So this is the result of the smartphone data, just including smartphone data. Here the BRITS model have significant higher accuracy. That is why I have just included the BRITS results. And the K equal to 4 means when it includes the 4 weeks of data together. So as we are using the QIDS and QIDS baseline as a comparison baseline, so the F1 score accuracy is 0.74, whereas when we add all of them together, the last row, that is EMA, location and medication, that is 0.73, which is fairly close to what we obtained from the QIDS score. Then for the QIDS baseline smartphone data, when we wanted to see the impact of the QIDS baseline with the smartphone data. So here again, we saw if we include the multiple weeks of data together, we found again enhanced accuracy. And when we add all the sources together, the last row, the F1 score is 0.75, which outperforms the comparison baseline, that is 0.73. And further, when we add the week 4 QIDS score, we saw enhanced accuracy in comparison to the other two scenarios. So here we found that when we add all the sources together, it significantly outperforms the QIDS baseline, so which is 0.77, which is fairly higher. So now in conclusion, here we have explored the first few weeks of data to predict the treatment 8 to 10 weeks in advance with the help of 2 deep learning models. And in the future work, we look forward to enhance the accuracy and implement some new advanced machine learning models to also to incorporate other data types such as phone app uses, communication patterns, maybe brain signals such as EEG and physiological signals to determine the improvement status more accurately. And also I do want to explore the feature ranking to understand which feature is most important in the prediction. Thank you. So here is the barcode of our paper. If you are interested, please scan the code to take a look at our paper. Thank you.
Let's thank the speaker, and let's move on to the next presentation. The speaker is Grace Lee. The title of the presentation is Game Connect, a middleware that flexibly connects games to their health goals.
Hello, so I'm Grace Lee, and I'm presenting Game Connect, a middleware whose purpose is to simplify the connection between serious games and sensors and the intervention. So this talk will walk through the motivation, the architecture, and the evaluation of the Game Connect middleware. So gamification has been shown to be effective in promoting healthy behaviors, but many of today's gamification apps are tightly coupled with the specific sensors and the specific interventions. So for example, if I were to play a game to encourage myself to walk more steps, but if I want to play a different game instead, then major rewrites are often needed. And the case is true for if I want to use a different intervention but play the same game. And so we asked what generic software is needed for flexible combinations between multiple games and multiple data. And so the answer is something that makes it possible to connect previously unrelated games to sensors and interventions in a way that we can just make minor modifications to the game so that it can reflect data from previously unrelated sensors. So why do we need the ability to connect previously unrelated sensors and data? And the reason is because you often see the same game appear in different interventions, and you also often see the same interventions but with different games. For example, this virtual tree game has appeared in many different places. For example, for the first one, if you drink a lot of water, your virtual tree will grow. And for the second one, if you walk a lot of steps, your virtual tree will grow. So this is the same game, but with different goals. And then there's also the case where the goal is the same, like a daily step count goal, but they're using different games. And so the key contribution of the Game Connect middleware is therefore twofold. First, it enables the data collection code and the game to run as separate and independent applications. And secondly, it allows any game that uses the Game Connect API to be connectable to any sensor whose data collection code also uses the Game Connect API. And so by doing so, we make it easier for these three actors to develop gamified health interventions without having to hard code every sensor and game pair. And so Game Connect sits in the middle. It takes in raw health data in the blue box and the health goal in the green box, and translate that into game mechanics on the far end. And so Game Connect provides separate APIs for each of these actors. For example, for the software engineer, she's in charge of writing the code that collects the data. And to her, the rest of the system is like a black box. And so there might be many different kinds of data sources, but they all boil down to the same, the value timestamp data source syntax. So Game Connect provides this generic syntax so that any data in this syntax can then be streamed into the Game Connect middleware using this insert raw health data endpoint. And so for the health domain expert, she doesn't need to care about the rest of the other actors. For her job is to decide the objective of the whole intervention, which is the health goal. And so Game Connect will compare the raw health data with the health goal. But how do we know how to interpret this raw health data? Because raw health data is more generic. It's just value timestamps, but health goals are way more nuanced. It could be something like daily steps data or weekly average steps. How do we know how to interpret this raw health data? And so that's where the data generating rule comes in. It takes in raw health data and translate that into more abstract information that ultimately becomes the language of health goals. And in addition to health goals, the health domain expert also decides how to map achieving a goal to the rewards that an end user will earn. And so for this, Game Connect provides two abstract types, point types, coins and lives. And this abstraction effectively decouples the health domain expert from the game developer. And so Game Connect generates lives and coins when goals are met according to what the health domain expert specified, and saves this lives and coins into a point pool. And the points in the point pool can then be accessed using the standard API, these three. This centralized point pool system allows multiple games to consume from the same pool of points. And because multiple games may interact with a single point pool, Game Connect ensures that the same coin or life can only be accessed once. And for the evaluation, we did a user study to answer some research questions. Our first question asks, is it easier to connect sensors? That is, we need to know if Game Connect can simplify the process of connecting a sensor to existing games, and if so, how? And then secondly, is it easier to connect games to sensors? And then the code that's related to the sensors, the code that's related to the games, and the goals, can these three be decoupled? And if so, to what extent? And so to answer these research questions, we devised 4 programming tasks using 2 data sources, the to-do list and the Withings activity tracker, and 1 game, the Catch the Fruits game. And so for each of these programming tasks, each participant needed to modify the game so that it can reflect data from the data source, and they also needed to write the code to collect the data from the source. We recruited 10 participants with varying programming experience. And so for our research question 1, results indicate that yes, Game Connect does simplify the connection process for the sensors. And so how? So as one participant described, the most the most frustrating part of this programming task was to write the loop that repeatedly queries the Withings API and aggregate the steps. So with Game Connect, in contrast, this was handled by the health data transformer. And so this reveals some of the challenges of working directly with commercial APIs, and also highlights Game Connect's efficiency in simplifying this process. And then our second research question asks, in what ways does Game Connect simplify modifying games in order to achieve the same health goal? And the answer is the point pool, because of the standardized APIs. And so this is what they had to do to modify the game to reflect the health data. With Game Connect, the modification is really simple, just an HTTP request to the consume points API. And then, so our final research question for Game Connect is, to what degree can the sensor goals, the game code, and the goals be decoupled? And so, as demonstrated by our programming tasks, each of these were developed by separate groups of people who were not affiliated with each other. And I sort of hinted at it earlier. With the programming tasks, the code for the game is dependent on the code for getting the data from the source. But with Game Connect, these two parts are completely independent of each other's. And some other things that we observed through our experiment was that people with more programming tasks, when they're doing tasks without Game Connect, they perceive the task as harder than people with less programming expertise. But if they can do the same task with Game Connect, people with more programming expertise tend to think it as easier. So this suggests that Game Connect amplifies a person's programming experience, and that it is a versatile tool for anybody with different programming skills.
Minutes left.
Okay, and so in conclusion, Game Connect is a middleware that provides flexible combinations between any game and sensors that use the API, and that the game and the intervention can be decoupled. Thank you.
Okay, let's thank the speaker so far. So we still have enough time for the next presentation. So the speaker is Kim Trott. The title of the presentation is Vibrant, Early Prediction of Life-Threatening Uterine Atony Using Maternal Heart Rate.
Thank you. I am not Kim Trout, but that's okay. I'm Jim Weimer. Kim is my esteemed nursing colleague. Okay, we've had 17 talks today. They've all talked about AI. This talk is not about AI at all. I lie a little bit. There'll be a little bit at the end for you, but it's more to show a point. And what I'm really going to get at here is use this as a kind of a discussion starter for hopefully during the coffee break of when it's appropriate to use AI and when maybe you should try something else. Okay. For the lawyers. All right. Motivation. Postpartum hemorrhage is the leading cause of maternal mortality worldwide. 80% of postpartum hemorrhage is a big loss of blood after the baby's delivered. 80% of that is caused by something called uterine atony. Uterine atony occurs whenever, after the placenta is delivered, the figure of 8 muscles of the myometrium don't cinch up and stop the bleeding, and then a bunch of blood oozes out. Most uterine atony events occur within minutes of delivery. This isn't 15 minutes later, this is a couple minutes later. There are delayed hemorrhages, and we can certainly chat about that later if you want to. Interventions for uterine atony exist. They're very effective, but only if they're administered quickly. And now we get into the problem. Timely intervention is critical to improving outcomes. Who here has worked in a hospital system? Well, let me tell you, the labor and delivery unit is a lost leader. It does not make money. So here what we have is the reason why we're seeing so many high hemorrhage rates, especially here in the US, isn't because we don't have the medications and the ability to prevent these things. It's because of an economic reason. We don't have enough money, the healthcare system, to spend on putting it across all patients. They cannot prepare for every patient to have a hemorrhage. They have to prepare for the ones that they think are going to have it. And that's the case in point. So State of the art. Kind of like two groups. One is the detection world of we're going to detect hemorrhages. The other is the prediction world where we're going to predict it before the baby's delivered. Okay. Detection side, I'm just going to say that yes, we can have a very fun conversation about delayed hemorrhage detection. It's a very important issue and we need to address it, yes, but that's not going after the vast majority of hemorrhages which happen within a few minutes of birth. So largely inactionable to do detection if you're telling the doctor who's already sitting there watching the blood out, hey, this woman's bleeding. Yeah, they know. Prediction techniques. The Joint Commission has mandated, Joint Commission does these sorts of things. In 2020, the admission risk screening be used as standard of care. 3 big ones out there, A1, ACOG, CMQCC. About 80% on the best of these, 80% of current postpartum hemorrhages are occurring in low-risk women. Okay, so now we got a gap. What do you do when you have a gap? You apply machine learning, right? And that's what everyone did. And hey, I always tell everyone, do it first. Might be a lot easier. If you can get to work, great, get through. But the problem has been there's been no widespread adoption for 2 main factors. You can talk to all the researchers in the world. At the end of the day, it's healthcare systems and people who fund medical device companies. Here's why you're having these issues. 1, lacks a turnkey solution. It's high integrate. I heard some people saying, oh, we just need to integrate with the EMR. That's about a $50,000 cost before you even see value. That's a problem. So no lack of a turnkey solution. You can't wheel it into the hospital, integrate with the EMR, and then all of a sudden see product. Now you can collaborate, you can do research, all great stuff. That's good. And that's one pathway. There's others. No method of action. This one comes down from the FDA. If you're going to throw a machine learning problem in front of them and say, look, I learned to predict postpartum hemorrhage risk, and look how well I'm doing, they're going to say, show me subgroup population bias. Show me all your secondary analyses. Show me your method of action. Okay, great, you used explainable AI. What does that mean? Right? They're going to hammer you on this. And it becomes very costly to build up the data set and to build up the information to do this. This is why I think we've seen no widespread adoption of these technologies to date. So what the clinical need is, in my opinion, is a turnkey risk prediction system that with a method of action. That's what we went for. Okay, method of action. Myometrium fatigue causes uterine atony. If the muscle gets tired, it may not cinch up after birth. Actually, this is well documented in the clinical literature. Fatigue is a reduction in muscle force. Cool. Well, there's many ways to measure pressure, and sports medicine people, we can argue about what EMG is measuring. It is measuring force if the muscle size is not changing, but everyone from high school physics, because we're not just throwing AI at everything, we know that force equals pressure times area, and as the baby is being delivered in phase 1, phase 2 delivery, the uterus is getting smaller, and so the shape is changing. The area is changing. If you're only measuring pressure and you're not measuring area, you can't measure force. That's just a fact. Okay. So the question is, can we measure myometrium fatigue another way? So what we've got so far is, I'm going to try to go for method of action. I need to understand why it's causing this, and that's because my regulators are sitting there, and I want to make sure I have an easier pathway through them. I want to de-risk my regulation, right? I can't have impact and have this stuff actually get out into the real world if I can't get past the regulators. That costs money. I want to de-risk that. Details are in the paper. I'm not going to bore you with a bunch of jargon, but I'll just say uterus contracts. We're going to use the cardiovascular system as a sensor. When the uterus contracts, about ½ liter of blood is injected back in as an autotransfusion. The less fatigued the uterus is, the stronger that autotransfusion is, right? It gets injected quicker, right? Just squeeze a Coke bottle or something. All right, that causes a change in cardiac output due to a process known as cardiac preloading. Cardiac output is stroke volume, how big your beats are, times how many beats per minute, right? That's your cardiac output. So whenever your uterus is less fatigued, you're going to see an increase in cardiac output that's larger than the cases where it is fatigued. Okay, great, but I still have the same problem. Stroke volume is something that requires like ultrasounds or something like that to measure. That's not a very turnkey solution. If I have to ask a nurse to go in there every 3 minutes and do an ultrasound, that's not going to work. So instead, we say, well, we found out that in late stage 1, early stage 2 labor, the stroke volume is generally always increasing. And if you see an increase in heart rate, you're going to therefore see heart rate increases with stroke volume. You don't see the opposite, because you can actually see an increase in cardiac output by seeing a larger increase in stroke volume due to cardiac preloading with a smaller decrease in heart rate, and that still would be an increase. So details are in the paper. But now we have something that gets us to heart rate, which is in fact a turnkey solution. I can get a heart rate sensor on anyone. I can walk into the hospital, attach an ECG monitor to a chest, no problems, right? This is straight, very easy to do. I can put a little dashboard display there that says, hey, this woman's at high risk or low risk. It's a factor, it all becomes CS work then, right? Get it up into the cloud, run an algorithm on it, do that sort of thing. Well, we have confounding factors. Heart rate increases during labor for a lot of reasons. So we applied some maximally invariant statistics and got to this sort of very convenient way of describing an algorithm. I don't think I heard a single algorithm today describe this succinctly, which is when both resting heart rate and contraction heart rate are decreasing, and this little metric here is also decreasing, then the parturient mother is showing signs of myometrial fatigue. Done. All right, there is the algorithm. Okay. We'll get to it. All right, so there's a data set evaluation. I'm not going to go through a bunch of details here. Just to say, sensitivity 83%, specificity 99%, or 90%, that's good enough. That means for monitoring about 10% more of your population, which hospitals are willing to do, that meets their price point. They're willing to monitor 10% more. We can take off about 60-some% of the hemorrhages. We compare it against A1. A1 is a admission risk scoring criteria. The key to this is understanding that the admission risk scoring criteria was actually used when we collected this data. Because when you're operating, no IRB in the world is going to let you not use their admission risk scoring system when you have two patients involved, mother and child. So you'll notice the A1 sensitivity was 0%. That's because the doctors were really good at preventing hemorrhages when A1 said high risk. That actually just proves my point. Right? And then details are in the paper. I make a whole impassioned argument to you about that. But the punchline here is A1 probably is a very good predictor. It's just the doctors are also very good when they know it's coming at preparing for it and preventing it. Okay? And yeah, it's 80%. In this case, we were going for life-threatening uterine atonies is what we evaluated against. Yes, we're not highly powered. Since this work was published, and since I'm presenting this work, yes, I realize 5 patients is not to claim 80%. There's a wide confidence interval there. Don't worry, we've shrunk that up significantly. Okay, so what have we done since we submitted this in December? It's been licensed. We've taken it through the FDA. We've learned that it's going to be regulated as a class 2 software as a medical device de novo pathway. Not having AI or ML on the de novo pathway simplifies things a lot. I'm not talking about necessarily in the radiology space, right, in images, that's okay. Time series physiological signal processing, de novo pathway, I encourage you to maybe consider whether you want to take on that challenge of proving safety and efficacy against the machine learning model on time series data. That can be challenging. Here, we don't have that. I have a method of action. Now, what are we going to do with this? Obviously, go on to clinical trial, getting that funded now, and to actually inform the effect side and then do the whole thing. So, future extensions. 1 minute. Perfect. Future extensions is to apply AI and ML. Why? I'll get better performance. I'm not stupid. I know that there's only so much I can actually do with my pencil and paper, mucking around with my team. No, but once we do that, we're going the 510K pathway. That is just proving substantially equivalent with what I already have here. Now what I've done is I've found a way to get to where I want to be, which is a learned algorithm that has better performance than what we're seeing there, that can predict risk and save women's lives. But I can do so by first introducing this surrogate system that also has very good performance and is clinically useful. And then use the 510K pathway to bring out the next one. So also, everything I did here, I'd love to chat about you. If there's anything you could have automated in this process, I would appreciate it, especially data labeling and data collection. That's it.
Thank you. Okay. Thank you. Sorry for the mistake on your name. Okay, let's thank all the speakers for the great presentation. And thank you all for your participation. So we may not have time for the QA session. So if you have any questions for the speakers, so feel free to talk with our speakers during the break. Okay, thank you all and enjoy your break.